company just down the Phillip Street. We make healthcare informatics products, especially in this office. It's for the PAC systems for the hospitals. Today we have the pleasure to have Dr. David Booth and come to ACFA and come to University of Waterloo and later to go to University of Toronto to give us a series of lectures. And this morning he had a lecture at ACFA talking about WSDL 2.0 new features. That is a web service description language, a new version which has been currently working on at the W3C. And Dr. Dave Booth has a very active role in the WSDL 2.0 working group, and he also a W3C Fellow, and closely working at the headquarters of W3C in Boston. And he's been very active in writing. I think you lead the effort in writing a primer in the WSDL 2.0. So you can, if anybody is interested in knowing more about web service description languages, and you can find the references on the web. And he's currently very much also interested in semantic web technologies. Semantic web technologies is a very major taking at W3C currently, and have a few working groups and actively working with the creator of web, Tim Berners-Lee. They're very closely working together. So my pleasure with Dr. Dave Booth.
Thank you, Helen. Okay, now the slides, I think we can turn that one off because I'm wired with one on my tie. Okay, which, as I pointed out earlier, it is now, I know, the reason why I wore this tie today. So, okay. The slides for this talk are on the web, and if you want to make a note of where they are for reference later, here's the long URL here. I also ran it through tinyurl.com to give a short URL, which is tinyurl.com/3VCQ9. So, I'm going to be talking today about a little bit about web services and a little bit about semantic web, and kind of making some connections between them to talk about the idea of global data reuse. Helen gave you a little bit of my background on slide 2 here. I work for Hewlett-Packard. I'm employed by Hewlett-Packard, I should say, although HP has placed me at the W3C working as a W3C Fellow. I've been doing that for the past 3 years, working out of the MIT office of W3C. Mostly on web services, but with a hand in semantic web technologies also. My background is in computer science. That's what I did my doctoral work in. And I've been doing programming for a number of years, using various operating systems over the years. Slide 3, a little outline of what I'm going to be talking about today. First, I'm going to talk a little about web services, and I'll mention what SOAP is, what WSDL is, and choreography, mention the need for semantics, and a problem that I call babelization. And then I'm going to get to talking about semantic web concepts, talk about what is the semantic web, a little bit about Google and the semantics of links, and then what an ontology is, and the use of URIs as globally unambiguous identifiers, and RDF. And finally, I'll just give some references for other connections between web services and semantic web. Slide 4, most of the ideas that I'm going to be presenting here are not my own ideas. There are ideas that have come from quite a number of people, and so I'm sort of indebted to lots of people that are colleagues at W3C and elsewhere. Slide 5. So W3C is an international consortium for specifying standards that are for the web infrastructure. Its mission is to lead the web to its full potential. There are quite a number of things going on at W3C, ranging from XML and HTML and digital signatures. Web accessibility initiative is a very important activity at W3C. That's to help ensure that websites and tools can be designed such that they are usable by people with disabilities. And I have to say, if you're not familiar with that work, do familiarize yourself with that work. One of the things that's interesting about it is that the principles of designing an accessible website, it turns out, are very applicable to people without disabilities, in addition to people with disabilities. They really, a lot of the principles just have to do with good design. So, web services is another area. There are a number of things going on in web services, including the SOAP working group or XMLP working group, which is now pretty much finished up. The Web Services Description Working Group that's been defining WSDL 2.0. I forgot to change the slide there. We decided to call it WSDL 2.0 instead of 1.2. Choreography Working Group, and I forgot to change this too. We've now started a working group on web services addressing as well. And here's another one I forgot to change. Evidently, I missed this slide when I was updating. And we have had at W3C a workshop on constraints and capabilities as they pertain to web services or policies affecting web services. And then another area of work going on at W3C is semantic web work, which has been working on RDF and web ontology language, and now a couple of other working groups, a data access working group for accessing RDF data, and a best practices working group. And there are other working groups also at W3C. So I just want to kind of give you the big picture context of how this work fits in with the overall work happening at W3C. Okay, slide 6. Now let me start talking specifically about web services. What I'll call traditional web application is an application that is designed to be accessed through the web by a person. So you sit down at your browser and you interact with an application at somebody's website. For example, you might make an airline reservation online. Okay, when you're doing that, you are a human sitting using your browser, interacting with an application over the web, and the browser is allowing you it's sort of facilitating that interaction between you as a human and that application. Okay, so that's a human-to-machine kind of interaction. Now, the idea behind web services is it's a machine-to-machine interaction over the web, okay, or a network. So you would have a web service that's providing some kind of service, and then a client application that wishes to make use of it, okay? And in the standardization efforts for web services, the efforts are involved in standardizing the ways and means of how to make that interaction occur, how to specify the interaction, etc. So it's essentially about machine-to-machine interaction. These terms, requester agent or provider agent, are just alternate terms. Different people call these things different things. Alternate terms for client application and web service. Okay. Now, web services is based on XML as a data format for both describing web services and for transmitting the information. But given that this is being built on existing web infrastructure, the existing web infrastructure was not XML-oriented. So when messages need to be passed back and forth between the client application and the web service, we'd like to be able to pass them in XML, but if the underlying protocols are not XML-oriented, what should be done? How should messages be packaged up in a convenient way? Well, slide 8, that's the basic idea behind SOAP. SOAP is a framework for representing XML messages. And it's intended to be layered on top of an underlying transmission protocol. Okay? So SOAP allows the easy sort of formatting of messages into XML to be able to conveniently indicate where the message is going and how it should be processed and that sort of thing. Now, the initial version of SOAP, or the most common version of SOAP that people are using today, is SOAP 1.1. That is a specification that was developed independently by a few companies and then put out for people to use. SOAP 1.2 has now been standardized to W3C and is built on those basic ideas of SOAP 1.1. Slide 9, the basic idea behind a SOAP message is that there's an envelope which acts as a wrapper for the whole thing. And then inside the envelope are perhaps some headers which might indicate things like who's supposed to be processing this message or how it's supposed to be processed, that sort of thing. And then a body. And the body contains essentially the payload of the message. Now, so a client and service and web service wish to be able to communicate using these SOAP messages. How can they agree, though, on what the signature should be of the message body? Okay, the schema for the message body. And also, how can they agree what transmission or transport protocols to use? Well, that's the basic idea behind Web Service Description Language, slide 10. Web Service Description Language, or WSDL, is a language for writing a description of essentially the interface for a web service. So when you write a WSDL document, that document is intended to govern the interaction between the web service and whatever clients make use of that web service. Okay? So you can think of it as being a sort of a contract between these parties of how they're going to interact. Okay, it's not a legal contract, but it's a formal description. It's a description that's written in an XML-based language that can be machine processed. And tools for processing the WSDL document can help to generate skeletons and stubs for the web service and the client that's going to be interacting with it. So in essence, then, the WSDL document is for specifying the syntax and the mechanics of the message exchange that will occur between these parties. Okay? The message formats, the data types, the protocols, that sort of thing. Okay? However, on slide 11, that's not all that's needed for a client to be able to sensibly make use of a service. A client is also going to need to understand the meaning or the semantics of the messages that are supposed to be transmitted. Right? It's no good to just send gibberish, right? Send messages that you have no idea what they're supposed to mean or receive them. You have to know what they're supposed to mean in order to make sensible use of it. Okay, so this is beyond what the Web Service Description Language, or WSDL, allows you to describe. WSDL is focused only on sort of the formats and the mechanics of the interaction, but not on the meaning of the interaction. Okay. It's a good idea, however, in your WSDL document to somehow make reference to, even if it's just a URL pointing to some other document that does describe the meaning of that of the interactions, the meaning of the messages that are supposed to be transmitted. Okay, so it's a good idea if the WSDL document references somehow some document. Now that document might be a human-readable document, or maybe it would be a machine-readable document. It all depends on how you choose to define it, okay? I'm not claiming that it has to be a machine-processable document. In fact, you might provide both a human-readable and a machine-processable document. But just in general, it's a good idea to make reference from your WSDL document to something that does provide the fuller, more complete information about how this service is supposed to be accessed and used, and what the meaning of the interactions are supposed to be. Okay, so that's the basic ideas behind WSDL. On slide 13, another area that I mentioned that the W3C is working on is the Web Services Choreography working group. That is a working group that's defining a language for describing for describing what one or more services is supposed to do. In other words, it's sort of a choreography of potentially multiple services acting together. Okay? So it could be a single web service, or it could be, let me distinguish distinguish choreography from what the WSDL describes. The WSDL language is limited to describing a single web service at a time and simple interactions, okay, such as just a request response. Choreography goes beyond that by allowing more complex interactions and by allowing you to define compositions of services. In other words, multiple services working together. And again, it is a machine-processable language that they're defining called CDL, Choreography Description Language. Slide 14. So the idea then is that you might specify a number of activities that are supposed to happen: shipping activity, customer activity, and manufacturer activity, that are supposed to be coordinated in some way. And there are kind of two different approaches to this general problem. One that has been characterized as orchestration, and the other is characterized as choreography. And the distinction is that orchestration, in the orchestration way of doing things, you have a single party who's responsible for directing all the others, okay? Telling them, okay, now you do this, now you do that, etc. So it's a single point that's directing all of them. Whereas with choreography, you don't have an individual party directing them. Rather, they are all directed by a common document, okay? That document is the description of what they are supposed to do, okay? And then they all work independently to achieve that. Okay, so that's the basic idea behind choreography. All right, so that was just a little sort of introduction to what web services is all about. Now, web services are getting a lot of hype these days. They're getting implemented. People are making use of them. So let's now think ahead a little bit, project forward and say, okay, so let's imagine what will happen now if web services become as successful and popular as, you know, a lot of people hope they will be, okay? What's going to happen? Well, if you think about it, a web service description, okay, a WSDL document, in essence is defining a little language for interacting with that particular web service, right? That's the idea. It defines, you know, the inputs, the outputs, the message schemas for that service. That's, in essence, a little language for interacting with that service, okay? So if we have now a proliferation of web services, what we have is a proliferation of these little languages, okay? Which is what I call babelization, okay? Here's an example. Suppose various different WSDL documents define different message schemas, etc., you know, using XML, and they define various different terms in their schemas. One of them might be publication author. Another one might be author. Another one might be document creator. Another one might be pub creator. Do these mean the same thing? Or is there any relationship at all between them? Maybe, maybe not. In general, the meaning, like for example, is author the same as document creator? Does that have the same meaning? Maybe. In general, the meaning might be the same, it might be different, or it might be related in some way, right? It might be similar, but not quite the same. So, the underlying problem here is that, on slide 16, the underlying problem is, or broader problem, is that it becomes difficult to reuse data, right? To make new uses of old web services or new uses of the data that's being produced by these things, okay? This is a common problem in a lot of places, trying to reuse data, right? Different branches of a government, for example, might have different, you know, silos of data that are all administered separately and are very difficult then to integrate together. It's very hard to make use of data across boundaries. Why? Well, because in general, the format and the meanings of the data do not necessarily match up. Okay. Slide 17. The root of the problem here is there are three possibilities. There may be different terms with the same meaning. Okay, so for example, one vocabulary might have used the term document creator, another one might have used the term author, but they might mean the same thing. They might really mean the same thing. That's not actually such a problem because you can have a rule that says these are actually equivalent. Okay? The second possibility is that you might have the same term with inconsistent meanings. In other words, same term being used here and over here, but they have different meanings. That's not good. Now you have a conflict. And you're going to have to somehow figure out how to prevent that clash. Okay? The third possibility is you have different terms and related but not identical meanings. For example, a document creator and author. Is it actually the same thing? One of them might have treated the term author as the individual who created the document. The other one might have treated the term document creator as the organization that created the document, or something like this. There can often be subtle differences, okay, like that. Okay. Another example is, let's suppose there's a term plane ticket and another term non-refundable plane ticket. So if I know something about plane ticket, what can I infer about non-refundable plane ticket? I mean, I should be able to infer at least that it's a kind of plane ticket, right? Even if I don't know very much more than that. I should at least be able to infer that much. Okay? Okay. So on slide 18, if you think about what is needed to overcome these problems, there are essentially three things that are needed. We need, in a machine-processable way, we need three things. Common vocabularies, unambiguous names for things, and common data model for expressing the information. Okay? Now, it turns out that these are exactly the same needs as for the semantic web. So let me now talk a little bit about what is the semantic web. Slide 19. The semantic web is, in essence, an enhancement of the current web. It's not a separate web. Okay? It's really just kind of an evolution of the current web, in which meaning is made to be more machine-processable. Okay, so that machines can do more of the grunt work for us instead of us having to do it as humans. Slide 20. So the overall high-level goal of the semantic web is to make the web more useful. Okay? Essentially, by making it easier to do three things. Easier to find, share, and combine information. In essence, what we're talking about is the idea of global data reuse, or being able to integrate data on a global basis. And the intended benefit here is to allow machines to automate more of the process that is usually grunt work for us. And there's a very nice quote by Dan Connolly at W3C who says, "The bane of my existence is doing things that I know the computer could do for me." Now, Dan Connolly, he's a computer scientist. He knows very well what the computer can and cannot do, from a theoretical point of view, right? And he knows very well that, every day he's doing some things, whether it's copying, pasting, or whatever, on the computer, that if the computer, were just programmed a little bit differently or something, it could be doing that work for him, right? So that is the objective of the semantic web. Is to allow it to do, more of the grunt work for us, to be more useful. So I said the objective is to make it easier to find, share, and combine information. So what do I mean by these things? Slide 21, the problem of finding information. Suppose you want to look for information on a person named Mary Cook. Okay? So you do a web search, and what do you find? Well, you got a lot of extraneous hits, right? You find out a lot about the Cook Islands. You find out a lot about cooking. Because there's no way to indicate that you are looking for a person with the name Mary Cook. Okay? The search engines are just doing a text matching, kind of thing. Okay, slide 22. What do I mean by the problem of sharing information? Okay, suppose I'm going to attend a meeting, and there's a web page that has a list of all of the people who are going to be at that meeting, and I say, okay, well, I want to put that list in my address book because I might need to contact them later. Put that list into my address book. Uh-oh, how do I do that? Okay. Well, the problem is I can't just grab the list and put it in my address book because the browser doesn't talk to my address book. Okay. The address book doesn't understand the web page. The web page is formatted for me as a human to read. Okay? So I end up copying and pasting, 47 times, email address, phone number, etc. Okay? So that's the problem of sharing information. Slide 23, the third thing is the problem of combining information. Here's an example. Website A has product reviews. Website B over there has product prices. I'd like to produce a list of product reviews with prices. How do I do it? Well, I write some nasty Perl scripts, right, that do some screen scraping off both sites, very fragile, break every time either site, changes in the slightest, and it's not very pretty, not very nice, very difficult to do, right? Okay, so that's the problem of combining information. Okay, slide 24. So the essential problem for why these things are difficult, finding, sharing, and combining information, is the lack of machine-processable semantics, right? That the computer doesn't understand the meaning or the semantics of the web pages that it's displaying to you, okay? Meaning on web pages is conveyed in human-oriented ways, right? For example, natural language like English, German, whatever is displayed. Graphics are used to convey meaning also on the web page. Even the page layout is used to convey meaning. For example, if you have a table, right, the position of some information within that table, indicates part of the meaning of that data, right? If it's in one column, it means something totally different than if it's in a different column of that table. Okay. So that's fine for humans to understand, but it's very difficult for a machine to be able to figure out what something means. And there's a very nice analogy here with a Gary Larson cartoon, which I'll show you. There's this guy who's scolding his dog. He says, "Okay, Ginger, I've had it. You stay out of the garbage, Ginger. You understand? Stay out of the garbage or else." And all the dog hears is blah, 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 Ginger, blah, 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 Ginger, blah, 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 Ginger. Okay? And, it's sort of like on slide 26, all the computers understand is blah, 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 ahref, blah, 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 ahref, right? The ahref does have meaning to the computer. It understands that. It knows that if it sees that on a page, that's a link to another page. Hey, I understand that. That's a link to another page. And if you click on that, I'm supposed to load that other page. But everything else is basically just kind of formatting gibberish that the computer does not make any sense of. It has no semantics associated with it. Okay? So we need to make the computer be able to understand more. Okay? Now, when I talk about the computer understanding more, I don't mean a human kind of level of understanding. All I mean is for the computer to be able to do useful processing for us. Okay? For it to be able to understand enough of it so that it can do something useful, some of the tedious work. All right. Here's an example of exploiting semantics in web pages. Slide 27. If you've looked into how Google works, when Google came out as a search engine, there were other search engines around like Alta Vista. Does it even exist anymore? Yeah, it probably does. I don't know, but who cares? Anyway, when Google came out, beat all other search engines hands down. Okay, why? Well, the reason was due to its ability to rank the importance of the pages that it was collecting. Okay, with other search engines, no matter what you searched for, anything, 5 porn sites would pop up, right? Why? It's because the porn sites were loading entire dictionaries onto their sites so that no matter what you searched for, they would show up. Okay? Now, what Google did was they managed to exploit the links that are pointing into web pages and analyze them in order to use those as a measure of the relative importance of those web pages. So here's how Google works, the page ranking system. They count the links that are coming into a web page. Now, I don't mean the links that are going from that web page to other pages, but what other pages are pointing into this page, okay? And they count them, and they're treated as votes. So, for example, this page has 3 votes because 3 other pages are pointing to it. Those are treated as votes of importance. They're saying that this one is important enough that I pointed to it. 3 three votes of importance. Whereas that one gets only 4 votes over here. And the votes are cumulative, okay? So this page got 3 votes here, and there's 2 more votes here plus the vote for this page itself. So this page down here gets a cumulative number of 6 votes, okay? Now, there's a little bit more detail, and there's a damping factor so that the numbers don't explode, etc. But this is the basic idea behind how the page ranking system works in Google, right? So when I do a search then, this one has more votes than that, so this one shows up at the top. Okay. Now, if you think about what they have done on slide 28, is Google has, in fact, exploited the machine-processable semantics of links. That's what they have done. Okay? Links are machine-processable, and they have semantics. Pretty minimal semantics, right? It's just semantics saying, this refers to that, okay? Which they've interpreted as meaning that thing over there is important enough that I've referred to it, okay? Even with those minimal semantics, they have achieved amazing results, amazing benefit just from exploiting those minimal semantics, minimal machine-processable semantics. So the thinking kind of goes, well, wow, if you can get that much benefit from just a tiny bit of machine-processable semantics, imagine what you could do if there was a little bit more machine-processable semantics available. Okay? So Bijan Parsia, who is working on semantic web technologies and is also a member of the WSDL working group, he, in fact, argues that Google is, in fact, an example of a semantic web application, even if it's not using RDF or the semantic web technologies per se. It is doing the essence of a semantic web application in that it is exploiting the machine-processable semantics of web pages. Okay, slide 29. So how can we enable more machine processing? Well, there are what I would kind of categorize as 2 different approaches you could take. One that I'll call smarter machines, and the other that I would call or characterize as smarter data. And I'm going to contrast these. Okay, slide 30. The first approach is smarter machines. The idea here is you teach your computers to understand the meaning of web data. You make them smarter, right, so that they can figure out what a web page means. Like you teach them how to do natural language processing and image recognition and this sort of thing. Okay. This is what I would characterize as the artificial intelligence approach. And this can be valuable. However, there's a little problem here that you very quickly run into very, very hard problems in computer science. Natural language recognition, for example, people have been working on for 40 years or something. I don't know. And the main improvements in the last 10 years or so have simply been faster computers, not really improvements to the algorithms, et cetera. So it's not easy to do this kind of thing. Okay? This is not the semantic web approach. This can be combined with the semantic web approach. Okay? But it is not, the semantic web approach is not dependent on solving hard problems like this. Okay. The second approach is what I would call smarter data. And this, is, in essence, is the semantic web approach. The idea is to make the data easier for the machines to understand. Okay? Make the job easier. Express the meaning of a web page or some data in a machine-processable format. Okay? So that's the basic idea behind semantic web. How do we do this? Slide 32. Well, again, the underlying needs are the same as what I called out before. We need, in a machine-processable way, we need common vocabularies, and that can be done with ontologies. We need unambiguous names for things. That can be done with URIs. And we need a common data model for expressing information, and that can be done with RDF, especially metadata. So now I'm going to get into each one of these 3 things in more detail. Slide 33. An ontology is, in essence, the experts in this area, of course, will each have their own definitions of what an ontology is. But for a sort of a broad brush definition, an ontology, in essence, is a formal description, first of all. It's a formal description, meaning that it's potentially machine-processable, of concepts and their relationships. So it's not just definitions of the concepts, but also the relationships between the concepts. Okay? Here's an example. You might have a definition of plane ticket and a definition of non-refundable plane ticket, and also the relationship between them. Say that a non-refundable plane ticket is a kind of plane ticket. So that's sort of a subclass relationship. Okay? Okay, so in other words, you can think of an ontology as being a sort of a common machine-processable vocabulary in some sense, although, again, with the relationships formally defined also. Oops. Slide 34. Some example ontologies. One well-known example ontologies is a very simple, basic ontology called the Dublin Core, which is an ontology for the area of publishing documents. And it defines it's only about 14 concepts that are defined in the Dublin Core. They're basic concepts like the title of a document, the creator of a document, the subject of a document, the publisher, etc. Another one is called OWL-S. That's an ontology specifically for describing web services in a formal way. And there are many others also. Okay, now, so this was one of the three things that I said was needed, just common vocabularies such as ontologies. The second thing I said was to be able to unambiguously identify things. So how can you unambiguously identify concepts? Well, in slide 35, URIs are very good to use as globally unambiguous identifiers. It's important to point out that a URI can have two very different uses. Okay? They can be used together, but they're very different. One is the URI can simply be used as an unambiguous name for something. Okay? Separate from that is it can be used as the location of a document. Now, typically, if somebody gives you the URI for a web page, they are using that to identify, to indicate the location of a document, because they're intending you to dereference that, to paste it in your browser, right, and pull up a document that's at that location. But even if you don't dereference it, it can still be used as a unique identifier, simply as a unique identifier. Okay? Another example of this is an email address. For example, I have an email address, dbooth@w3.org. That's my W3C email address. You know, if you are talking about somebody whose email address is dbooth@w3.org, and then you're talking to a colleague over here who says, oh, yeah, I know a person whose email address is dbooth@w3.org, you know that you're talking about the same person, right? Because at least at a given point in time, email addresses are unique. And I will sort of stand on a soapbox here and say they should not be reassigned or reused. But some companies do, in fact, reuse email addresses, which is bad practice, I think. Anyway, so that's an example of something that is an unambiguous identifier. Okay? Now, it doesn't tell you where I live. It doesn't tell you, really much more about me, but it's used as an identifier. So once two people know that they're talking about the same person through that identifier, then they can combine what information they have. So the point is that the name as a globally unambiguous name is still useful even without accessing a location. Okay. And for this reason, URIs can be very helpful in identifying concepts in an ontology. You can make up a URI for each concept in the ontology and use that as a globally unique identifier. And to be friendly and convenient, you can also put a document at the end of that URI that describes that concept that you are defining. Okay? So it makes it a very, very convenient way to have a sort of a self-describing concept in some way. And I like to make an analogy with when people were learning HTML, when the web first came out and lots of people were learning HTML. A lot of people learned HTML and continue to learn HTML by when they look at a web page somewhere and they say, oh, that's kind of a cool trick. How did they do that? Well, in the browser, they just do a view source, and they see the HTML and say, oh, yeah, there it is, right? That really facilitated the people learning HTML very quickly. And this is a similar kind of, I think, facilitating idea that if you use a URI as a globally unambiguous identifier and you put a document at the end of that URI also, it makes it a very convenient way to document the meaning of that term, that URI. Okay, slide 36. Here's an example of URIs being used as identifiers. So I'll make up this URI here, example.org/staff-IDs #85740. Now, that might represent, for example, an identifier for a particular person. Okay? Here's another one, http://perl.org/dc/elements/1.1/creator. That, in fact, is the URI that unambiguously identifies the Dublin core ontology concept of a document creator. Okay? So if you're talking to somebody else and you're talking about, and you identify this concept using this URI, there is no question about what concept you're talking about. You are talking about the Dublin core version 1.1 concept of creator. And if you paste that URI into your browser, what do you suppose happens? You get a document that says what that thing is all about. Okay? Very nice. So one overriding piece of advice I would have is use URIs as unambiguous identifiers. They are very, very convenient and helpful to use in this way. Globally unambiguous. Okay. Slide 37. There is a technical issue being discussed within the W3C technical architecture group. And the name of the issue is called HTTP range 14. And there is a URI that identifies that specific issue, by the way, of course. And the issue has to do with if you look at this URI here, example.org/danscar, is that thing supposed to be identifying a document that's at that location, or is it supposed to be identifying a thing that that document describes? In other words, Dan's car, Dan's actual car. Well, there's a convention that Tim Berners-Lee, the inventor of the web, and other people encourage, which is to use the fragment identifier. The fragment identifier in a URI is the part that is set off using a hash sign if you are identifying the thing rather than the document. Okay? The controversy, the HTTP range 14 controversy, is all about whether that hash sign is really needed. Okay? Because if you know the context of how this thing is being used, then you may be able to know that they're talking about either the car or the document. Okay? But if you don't know the context, then you might not know actually which one you're trying to refer to. So by using the hash sign, you're safer, you are very clear as to which one you're talking about. So my advice to you would be, go ahead and use the hash sign. There's no loss in doing so, and there is certainly potential gain. Okay, slide 38. So we need to have ontologies and use URIs to identify the concepts in those ontologies. Does this mean that we should standardize one big ontology that everybody would then use so that everybody could have kind of common language and communicate? Well, that's not realistic or practical. And in fact, there's a good example of this. Libraries have been around for hundreds of years, right? Libraries have their own ontologies. They have card catalogs, right? Even today, different library systems use different classification schemes. Okay, so even after hundreds of years, they still cannot agree on a single ontology for libraries. Okay, so clearly there was no hope in having a single big ontology defined by some never-ending committee or whatever. Okay, Option 2, allow arbitrary conflicting ontologies. Well, obviously, that's not such a good idea either to have conflicting ontologies. So option 3 is the sensible alternative. This is a realistic, and this is really the way things are happening. Allow multiple ontologies. This is natural, this is normal, and this is actually a good thing because different domains have different kinds of expertise. And they need to be able to define their ontologies in their domains of expertise. But if they use URIs to identify the concepts in their ontologies, then they can be globally unambiguous. Okay? And this makes it, this facilitates then the possibility that they can later be combined as needed into larger ontologies. So you find one ontology over here that has some of what you want, and another one over here that has also some of what you want, and you can start making use of both of them. Okay? Now, combining ontologies, if they have overlapping concepts, is not necessarily easy. There is some work on trying to automate the process. But in essence, some of the work must be done manually and is not easy, okay? Because different people simply defined different concepts that are a little bit different, right? They might be kind of similar, but not quite the same. And so you have to work out what are the connections between them. Okay. But if the concepts are identified with URIs, then you can avoid those accidental conflicts that can occur otherwise. Okay, slide 39. So at W3C, there's a working group called the Web Ontology Working Group that has been defining a common language OWL for writing ontologies. And this will also help facilitate the ability to merge ontologies. Because even if they are different ontologies, if they are written in this common OWL language, then it makes it easier to connect them up. And the OWL language is it's one part of the semantic web activity. It's actually now reached its recommendation status at W3C. And it is based on RDF. So now it's time for me to talk about RDF. Slide 40. So what is RDF? RDF stands for Resource Description Framework, or at least that's what it stood for initially. But I think it's more informative or more useful to think of it standing for relational data format, or perhaps reusable data format, because those, I think, are more descriptive of what RDF is really about. RDF is also a W3C recommendation, and it's actually been out now for about 5 years, so it has some maturity. It's a language, it's a very general purpose language for making statements about things. It's typically used for metadata. Things like, for example, in the Dublin Core ontology, indicating the author of a publication or the title, etc. It has an XML syntax, but RDF itself is actually above the syntax level. In other words, there is a syntax for expressing RDF, but there can be other syntaxes also for expressing RDF. RDF is a data model, right? Okay. So it's basically a simple universal data model. Slide 41. RDF is based on triples. In other words, when you want to make a statement in RDF, it's a conjunction of three things. You can think of the triple as representing subject, verb, and object of a sentence. Or if it's more convenient, you can think of it as representing subject, property, value. Okay? It's just a group of triples together. Each statement is just a group of triples. And all three of these three things, the subject, verb, and object, can be URIs, so they can be globally unambiguous. Slide 42. Here is an example of an RDF triple. Now, I haven't actually written down the RDF XML syntax for it because I don't care about the syntax here. But here is the triple. The triple is formed of these three URIs. The first one is the subject, and I've written the URI for a document, foo.html on some website somewhere. The second one is that Dublin Core URI that I showed you that represents the Dublin core concept of a document's creator. That's the verb. And the third one is that example, the URI that I made up that identifies some particular person. Okay? So in essence, this triple is like a sentence that says, web page foo.html on site example.org was created by this person, you know, John Smith or something, some person with that staff ID. Okay? So that is the idea behind an RDF triple. Each RDF triple just represents a little statement. And you can have, you know, when you have then lots of RDF triples, then you have lots of statements. Okay? Okay. So, slide 43. There are two views then, or perspectives, about the use or purpose of RDF. And I want to just kind of contrast these. One perspective is that RDF is kind of the basis for Tim Berners-Lee's vision of the semantic web, right, in which it's an enhancement of the current web in which the information is more machine processable. Okay? That's one view. It's one of the sort of enabling technologies to achieve the semantic web vision. But there's another view of RDF entirely, and that is that it is simply a technology for solving data integration problems that you can apply right now to specific data integration problems that you might have. Okay? This distinction between these two viewpoints is very important to understand, because there are, you know, a fair number of people who look at the concept of the semantic web and say, yeah, that would be neat. You know, wish I could do that now. And then assume that there's no benefit of RDF, you know, sort of until we reach that point where, you know, there's a lot of it on the web and then we have the semantic web. And that is simply not true. RDF has applicability in specific areas right now, okay, that is even independent of the general semantic web vision. Okay? And this is in fact one of the reasons why we are seeing you know, more and more applications now making use of RDF. Okay, so slide 44. I started off this talk by talking a little bit about web services and pointed out that that if you think ahead and you think about what's going to happen if web services become popular, you're going to have this problem of babelization, and how do we solve that problem? And it turns out that the same tools or same principles are needed to solve that problem as for the semantic web. Historically, the web services community and the semantic web community have been mostly separate, you know, kind of different groups of people working on things. The web services community tends to be a bit more business-oriented, more focused on immediate products. The semantic web community tends to be a little bit more academically oriented and a little bit, you know, more of a longer-term focus. But there is crossover between them, and in my opinion, there's actually a lot of potential benefit for, you know, for more crossover between them. There is also, slide 45, work going on in applying semantic web principles specifically to web services, like, for example, describing the semantics of a web service formally using RDF. Okay, so here are some references for some things going on that kind of make connections between RDF and web services, if you're interested. All right, and slide 46, this brings me to the end of my talk. So I've been talking about web services. I talked about the problem of babelization if they become popular, each WSDL document describing, in essence, a little language for a web service, and the problem of trying to connect them up later on. And then I got into into semantic web and talked about how we need three things. We need ontologies, we need URIs as globally unambiguous identifiers, and we need a common data model which can be solved using RDF. So at this point, I'll throw this open to questions.
What I'd like to do is to pass the the microphone to you, so if you'd be patient, I'll get it to you. Questions or comments?
I can also repeat the question. Yes.
Introduce yourself, by the way. I'm Yuri Kogolovsky. I'm from Conestoga College. Thank you very much. I think it's a wonderful talk. I have a question about ontologies.
Yes.
So one of the things is that how are you going to update ontologies? I totally agree with your approach that it's impossible practically to create one ontology that would satisfy everyone, although there are people that do try to create such global ontologies in any areas, like including medical informatics or any other areas. Now, I agree with you that it is probably the best way that different ontologies will exist. But the question is, how do we update ontologies? Because terms change their meaning with time. And human beings usually do this based on the context. The context is taken in account. With ontologies, we don't do this. We kind of widely defined every term in ontology and relationship between them. So my first question would be related to this.
Okay.
So how to update ontologies? How do you see this?
So there are, in essence, two questions. One being how do you update ontologies, and the second one being, sorry.
No, it's practically one question. Like if how to update.
Okay,
ontologies.
so updating ontologies. Oh yeah, about context, right? That was the other thing I wanted to hit on. How do you update ontologies? Well, first of all, I would say that. Actually, let me comment about context first. Context-dependent meaning is bad. Period. Okay? I mean, it just causes problems. And, you know, especially, I mean, that's kind of one of the underlying themes of the semantic web technology is to make the meaning be clear and unambiguous globally, right? So that it is not dependent on context, right? So that the same term that you find over there, you know, in some ontology over there, or that somebody else has used in one application, means the same thing as that same term used in some other application, okay? If it's unambiguously identified by a URI, then you can achieve that, okay? So, yeah, so context dependency is not good. On the other hand, it's impossible to avoid. The fact is, context dependency will always exist. And so really what we're trying to do is minimize it, right? The kind of context dependency that I'll point to that will always exist is, suppose you have a URI that is totally unambiguous, identified by, I'm sorry, it's a URI, so it is globally unambiguous. And you make a statement here. One person makes a statement over here and says, the sky is blue, globally unambiguously using URIs. Somebody else over there makes another statement that says the sky is green. Okay? Those are completely unambiguous, but they are probably not both correct. Okay? So what's happening here is, in order for me to make sense of both statements together, I have to know something about their context. I have to know something about their provenance, right, of who said them and who am I going to believe. Okay? That kind of context dependency we will never get rid of, right? But the other kind of context dependency of, you know, just the same term being used in different ways in different, you know, contexts within a sentence, that we can get rid of and should get rid of. Okay, so now a comment about versioning. So in general, with versioning, what you want to do is not change the meaning of any existing term. Don't change it. Okay? What you do is you make up a new term that has a little bit different meaning, and then you indicate the relationship to the old term so that they both coexist. And this gives a very graceful versioning evolution, if you're able to do it that way. Because changing breaks things, So that's what you want to do.
Yeah. The only thing is that, I agree with you, the only thing is that the terms evolve usually. You see, if there is no automatic way to update ontologies, then what can be a problem is to realize that the term in ontology has really changed the meaning. What I'm saying, for example, let's say the term malaria. Previously, this term meant bad air. Now
Yes.
we have something associated with this term related to specific kind of disease.
Yes,
Another
that's a good example.
Another example, let's say we have term gastritis.
Yes,
This term
so-
would mean totally different things for a general practitioner, for pathologist, for imaging specialist, and for somebody else. You see, the
Right.
thing is that if we
Yes.
cannot do this automatically to identify that there is a time when we have to change the meaning of the term in ontology, as well as preserve other meaning. So how to do, my question was how to do this gracefully and automatically.
Okay, so I think what you want to do, though, is, the malaria example is a very good example. The word that we use in English, malaria, originally meant bad air. I've forgotten whether it was Latin or Italian or something. Latin, yeah, okay. Latin and Italian are very similar, actually. But I speak some Italian, so. But now it's come to be, a medical term for a specific disease, right? The problem there is that the meaning of that term was not defined, okay? The problem is not that the, let's see, how do I put this? It's not that the concept changed. It's that that term was at one point used for one concept, which meant bad air, and at a later point, that same term was used for a different concept to mean a specific disease. So when you're defining ontologies, you don't want to do that. You want to, first of all, you need to define the meanings of the terms. The use of a word does not, the mere existence of a word like malaria does not define it. You have to actually spell out separately what that thing actually means. And then avoid changing the meaning of that term. Don't change the meaning of that term. If you want another concept that means a disease rather than bad air, make up a new term for it, right? And then, again, indicate the relationship. So, other questions?
My name is Shadi. I'm from computer engineering, electrical and computer engineering. I have a question regarding the evaluation of the ontology. Is there any standard way to evaluate ontology?
Is there a standard way to evaluate ontologies?
Yeah, except using it in a special application. It's a very specific domain application. Is there any standard way to know that this ontology is very large or can be used for?
I don't know of any standard ways to evaluate ontologies. You can do things like check an ontology for consistency, right? See if it contains any internal contradictions, for example. But beyond kind of basic, fundamental checks like that, the big question is, I would say the big questions are, one, the appropriateness of that ontology for your specific use, and two, the clarity by which, the clarity by which the ontology is defined. Like, are the terms clearly enough defined? And I guess a third thing, which is related to the appropriateness for use, has to do with the granularity of it. Is it at the level of granularity that you need? Because you can drive yourself crazy trying to define, in great detail, certain concepts that can go way beyond the need that you actually want to apply them to. So designing an ontology is not necessarily, I would not say that it's easy to design a good ontology. It takes good judgment, and it takes knowledge not only of the domain, but knowledge of what you want to achieve from that ontology. What use do you want to put to it, right? And so, for example, the Dublin core ontology, which is very simple, limited itself to some very simple concepts. They don't spell out, in further detail what, for example, a title of a document is supposed to consist of or what it really means. Okay. So, choosing an appropriate level of granularity or detail is one of the arts of designing a good ontology. Yes, Helen.
Just the same. May I just also add that the semantic web enable that you be able to easily add more concepts or add more explanations to a concept you originally defined. You will not break your previous application or whatever. So that make it very scalable. So you really don't have to have that cut at one shot, right?
Right.
And you can they become some very additional. So in an additional manner, when you have some rules to deduce certain new facts, or you add certain new descriptions, properties for a particular concept, that's actually very easy to use in the semantic web.
Yeah.
And also, can you commenting a little bit on the concept mapping as well? Between different ontologies, if they talk about the similar things, you can really mapping your concept between
yes,
two.
Not necessarily easy to do, but you may be able to. Let me just mention a good example of that might be, for example, in the medical field or healthcare. Maybe there's a disease that's identified, and at first you only know a little bit about it. Right, but you put it in an ontology, you make up a globally unambiguous identifier for that disease, right? And then later on, as you accumulate more information about it, then you can add to that ontology, add that information. Okay, now at some point you may realize, oops, that wasn't one disease. That was actually 3 different diseases that we thought was a single disease, but there's actually 3 different ones. Now what do? Because now you have this single globally unambiguous identifier that is now ambiguous in some sense because you don't know which of those 3 diseases it's identifying. What do? Well, that identifier still identifies, it's sort of a disjunction of 3 diseases, right? That it might be this, it might be that, or it might be another. What you need to do then is add 3 new identifiers. You don't throw away the old one, but add 3 new identifiers now for the new diseases that you've identified and indicate that those are related to the old identifier in this way. So, yes.
My name's Mayor Tanwan. I'm from Conestoga College teaching there, and I'm a grad student here at Waterloo. My question revolves around what are some of the research areas that you could find in semantic web. In particular, I'm interested to know, has the RDF data model been validated? Like, how powerful is it? Can it really express all these complex semantics?
Yeah. So you're wondering how powerful is the RDF data model? The data model itself is very simple, but you can ascribe, much more complex or much more. You can ascribe powerful semantics to it. The web ontology language, OWL, is built on top of RDF, and it's used for writing ontologies. And there are 3 sort of levels of the OWL language that depend on the, depends on the degree of power, the degree of expressivity that you wish to have in your ontology. If you limit yourself to OWL Lite, that's the least expressive, but it has certain properties of being able to be, I've forgotten exactly what the properties are, but it's nicely machine processable. Let me put it that way. In reasonable processing time. I've forgotten exactly what the criteria are. And then the next level is OWL DL, and that has another threshold, and I don't remember exactly what that is. And then finally the third one is OWL Full, which is very powerful, but is also undecidable. Okay? So you can choose the level of expressivity that you want. Okay? Description logic. Thank you. Yes. Yes. Yeah. OWL is for description logic. Yes.
My name is Khalid, and I'm a Ph.D. student in systems design engineering. My question is a bit of a technical question. It has two parts. The first part, are there any tools currently available to start enriching web pages with RDF or semantics? And the other part is about tools as well, but tools for using the semantic web, like semantic browsers or semantic search engines, things like that.
So tools both for producing RDF and for consuming it. In terms of annotating web pages with RDF, that's still, people are still working on sort of defining what are the best ways to do that. And there are proposals. I think, one proposal that kind of has probably the most momentum is called GRDL, and I forget what it stands for, GRDDL. It basically allows you to have a document that references both a human-readable description and an RDF description. And in terms of, but I want to point out that that most of the RDF data is not likely to come from individual web pages that have been annotated with RDF. Most of it is likely to come from databases. Okay? Databases already have their data in a very nicely structured format. So it's quite easy to simply expose that data in RDF. And it turns out that a lot of the data that's on the web is in fact coming from databases. So it would not be difficult to put a layer there to expose that data as RDF. Very easy, in fact. Now, with respect to tools for digesting RDF and making use of it, yes, there are browsers for making use of RDF. There's one called Haystack, and there's two or three others also that people are working on. But these are also continuing areas of research and stuff. Yes.
One of the things that I just wanted to bring to your attention, maybe, or just hear your opinion about this, is the data from cognitive psychology part. It was demonstrated that different like if you have ontology and all other nice things that you have here with any kind of resource, including web resource, it assumes that the users of these resources would have the same structure of ontologies and the same understanding of structure related of these triplets, right? Otherwise, there is a mismatch between semantics of a document and a creator who will press a user to follow this kind of semantics. The same. Do you understand what I mean?
So you're saying that that in order for an ontology to be usable, the creator of that ontology has to have the same notion of the meanings as the user of that ontology?
Exactly. What I'm saying is practically that semantic web would work for a specific user, only in a case if semantic web of a creator is the same, the semantic structures of a creator is the same as the semantic structures of a user. Otherwise, what will happen, there are two options, three really.
Right.
They match approximately and the user would be satisfied. The second one, they totally disagree and the user does not use the structure because it's totally different semantics. Yeah. And the third option is that it's practically what's happening now with the way how computer user interface works, that people are hardly pressed to use the semantics of an interface, and when they disagree with this, they just abandon the whole story.
Yeah, you're absolutely correct that the creator of the ontology and the user of the ontology have to agree on the semantics, yes. So how does that happen? How can that happen? Well, in essence, the issue there is how can you define ontologies in a way that are very clear, such that their meaning is very, very clear, and will not be subject to interpretation by different people, right? That two people reading the same ontology independently will understand the same thing. Okay, so part of the design of RDF, I mean, I don't think that RDF is unique in this, but any formal language that is used to try to define semantics, part of its objective is to achieve that, is to facilitate the definition of concepts in such a way that they will not be misunderstood by somebody else. And the degree to which that language is successful, you have to make that judgment as to how successful you think it is. I think Helen Chen and her colleague were asking me a question at AGFA about a comparison between XML and RDF in terms of, what's really the benefit of RDF over XML? And that, I believe, is actually one of the benefits of RDF over XML, is that I believe when you're using RDF, it encourages clearer descriptions of the meanings of things, what you're defining. And it would take a bit more explanation for me to explain why I think that, but I do think that's the case.
Yes, Stan Devitt, researcher at AGFA Healthcare. And I want to add a comment that may go partly to addressing the last question that came forward as well. And that is a very, very important part about the semantic web and RDF, and in fact something that was very fundamental within the semantics and content ML as well, is that by using a universal identifier to very clearly indicate that this is the concept that I mean, right up front, you're giving the reader of that data, whether it be machine or human, the opportunity to say, oh, you're talking about a different concept from the one I have in mind. And it's very, very fundamental to the concepts that you've added this one extra piece of information. You're actually tagging it with a definition.
There are a few assumptions here. I agree with you to the point, but there are a few assumptions here. One of them is that this kind of view accepts from the very beginning that we can clearly identify concepts. But unfortunately, based on cognitive psychology part, it's not the case. We cannot clearly identify concepts. And what shows cognitive psychology demonstrate that we really clarify concept based on context. Because when we see concept, the only way we usually understand what is it all about is that when we parse and it gets into our short-term memory, the terms that are around this concept based on semantics of syntaxes and semantics of language that we use, this is how we identify concept. So first of all, we do this by context, and the second thing, we never can do this precisely enough. We can be wishy-washy, and this is another problem that we cannot explain. And such kind of work I have been following such work done by different people in medical informatics or in nursing informatics in different ways with control terminologies. And there were a lot of projects, including Galen Group and some other groups, that unfortunately did not result in a very good, did not receive good results. This is one of the problems. So
I think you're right that I mean there definitely is a degree to which the meaning of to which RDF is not going to help you better define the meaning of something than anything else is. Yeah, I think you're right, and I don't have a solution for that kind of problem. So, yeah.
What I'd like to do is, rather than going into greater depth about this, is put Yuri and you and Helen and you together at the end. And Yuri's had a long-term background in this area. I've known his work for many years. I think that the discussion with him will bear some interesting fruit. I want to make sure there aren't any other topics that we need to cover before I end this, because we're getting right to the time. Any other? Okay. Well, just a couple of comments. First of all, it was interesting to me when you had your first slides up with those mistakes on it. Unlike many of us academics, you actually did the things you said you were going to do. So I thought that was quite impressive. I also have this vision of the gymnasium of universities with millions of email addresses hanging from the ceiling as they retire each email address in the place. And, you know, very good. I just wanted to comment. I thought that was one of the clearest presentations I've heard in my life. Absolutely fantastic presentation. Thank you very much.
Thank you.